So a short introduction about me. I guess a lot of people who already visited any of C++ Siberia or C++ Russia know who I am, so I'm going just to skip this slide. And I'm going to move to my favorite quote by the Lambda man that you have seen yesterday on Alex's talk. Make your code readable, pretend that the next person who looks at your code is a psychopath and they know where you live. So if you remember the guy in the Superman outfit with a lambda, that's the author of this quote. So introduction. As we all know, C++ is a general purpose programming language. And sometimes we have to deal with some specific domains where a general purpose language is not really well suited for them. And usually we create something that is called a domain-specific language. So we design a programming language that works just for a specific set of use cases or a specific domain. And we have a lot of those. So we have SQL, a domain-specific language for querying tables. We have regular expressions. We have, I completely forgot what's the name of the thing where you define grammar for a language. It's Bacchus notation or something like that, right? So all of these are some kind of domain-specific languages because they're designed just for one thing in mind. They're not general purpose. Now, the problem with normal DSLs is that you either need to have a separate tool to compile them, or you need to have the string-based semantics in your host programming language, which is the most common use case for SQL and for regex, which means that when you compile your program, you have no idea whether you made a mistake inside of your SQL query or in the regex. So it's common, well, not common, but it's a good idea to try to embed some of these domain languages into your host language so that they're not strings inside of C++, but to actually have a valid C++ code, some subcode, let's say, some library that implements internally language inside of the C++ programming language, so that the compiler, when you compile your code, that it compiles the domain-specific language as well. With C++, it's a little bit difficult to create really advanced DSLs because we are kind of limited to the usual object-oriented notation, something dot something. The good thing is that we can overload operators and that we can use braces and parentheses inside of our embedded DSLs. Now, recently, we've got a new operator that we all love to call the spaceship operator. In some languages, you wouldn't wait for the committee to vote in a new operator, then the compilers to implement the new operator. You would be able to create a DSL that has operator called a ship on the sea next to a mountain with clouds and the sun. And this is the operator that you could implement in some of the other languages. Now, C++ doesn't allow you to do so, which is both a shame and a really good thing. So it's a shame because this would be a really cool thing to have in your code base. And the good thing that C++ doesn't support something like this is that, for example, in Haskell, where something like this is allowed, all the libraries create fish operators, then fish operators that eat other fish operators and stuff. So the code becomes really, really unreadable. In C++, every DSL that you're going to create will have to look a bit like normal code in C++. So let's start with a simple example. Just imagine you want to update an object and you're updating several fields, several members of said object. What happens if an exception is thrown when you try to update, for example, the second field? Your object is left in an unspecified or invalid state. You updated just the half of it. And a lot of bugs in computer programs are due to invalid state. We have an idiom in C++ that allows you to assign several things. And if the exception is thrown, nothing happened. It's like nothing happened. And if no exception is thrown, then the complete update has been successfully performed. Now, this idiom is usually used with the assignment operator, and it's called copy and swap. What's the idea? The idea is I'm not going to change my object. I'm going to create a temporary copy, change the temporary copy, and only if all the changes are successful, then I'm going to swap myself with that temporary object. If the copy didn't succeed, for example, the exception was thrown, our original instance, this has not been changed. We can use the same idiom to ensure that we never update our objects just partly. We can create a temporary copy of the user, update it, and if all the updates succeeded, then we can just say, okay, swap the temporary and the actual value. And obviously, for this to work, swap can never throw an exception. So swap always needs to succeed. The problem is that this is kind of boilerplatey. For each of the updates, you need to create a copy, then do the updates, then do the swap. We can create a small DSL that would look something like this. So with user, perform the following updates. Now, in this code example, we've used just parentheses, we've used operator equals, which means that this should be possible to implement as a DSL inside of C++. This looks like valid C++ code. Just a little bit strange, right? So if you were to analyze the syntax of this thing, we can see that we have something called with that looks like a function. So it's either a constructor or a function object. And it returns something that also looks like a function. So the with object can be called with parentheses, and the result of it also can be called with parentheses. Fine? Now, the next step is to analyze what's inside of the second pair of parentheses. We have name equals Martha, surname equals Jones. So we have a list of items that we need to update, and all of those update actions are defined by what we're updating and the new value that we want to assign. So if we were to draw the abstract syntax tree of the previous expression, we would have the with object as the root of our AST, and we would have operator equals that joins a field and a value, operator equals that joins a field and a value, and the third time the same. So let's start with, with the root of our AST. It only needs two things. It needs a constructor so that it knows on which object it will perform the updates, and it needs the call operator, and we are going to pass the updates to the call operator. For the time being, we don't care about what the call operator does. We just want to implement the syntax, not semantics yet. So the call operator will take a list of actions to perform. Obviously, this will be a periodic template later on. So we have implemented the syntax for the root. Now we need to implement the syntax for all of the update actions. So each of the actions has a name, a field that's going to be updated, and a value that we want to assign to it. So if we wanted to model this node in C++, we would just create an update class template, and we would say, okay, it contains a pointer to a member, and it contains the future value. Now, note that an update doesn't know on which object it works on. So you can define an update once and perform it on as many objects as you want. It doesn't need to. If we look at the abstract syntax tree, this rectangle doesn't need to know what's inside of with. Now we have implemented the node. Now let's implement the syntax. For the syntax, we can just say, okay, this should be the result of some assignment operator. So let's create a structure called field, again, a template, and it will get the pointer to member on the construction, and it will get the new value when you call the assignment operator on it. So we have implemented the whole AST. Easy so far. So this is the syntax. After the syntax comes the semantics. Usually you will want to separate the syntax of your DSL and the semantics. In this case, because we want to create a simple DSL and we want to perform the update as soon as the call operator on vid is invoked, we are going to implement the semantics inside of the class that we've previously created and called transaction. Now for semantics, we need to deduce what transaction for us is going to be. Is it a database, so it's something rollback or something commit? Or do we want to deal with exceptions like in normal C++? Or maybe all of our update actions, when called, will return a Boolean value saying true or false, depending whether they succeeded or not. So for this small example, I've decided to go for each of the update actions are going to have a call operator, and the call operator returns true if the update succeeded and false if it hasn't. So when we define an action and say update action name equals Martha, if we invoke it on some user, it will return bool if everything is okay. So with our transaction, we can create the periodic template call operator, and we are creating the temporary object, just like in the previous examples. Now, we need to call the update, all the updates that are specified on our user. In C++11, this would be quite a tedious operation. We would need to have some kind of compile time recursion to process all the periodic template arguments. In C++ 17, we've got fold expressions. Now, I'm just going to shortly state what they are, but you're going to listen more about fold expressions on the Oleg talk, the next one. So in C++ 11, when we had periodic templates, we had the possibility to create a function that accepts multiple arguments. And if we wanted to expand those arguments to say the compiler, okay, write them all one after another, we would be able to do so only with commas in between them. So when we call functions, when we call create initializer lists or anything else. With fold expressions, we can put any C++ binary operator in between the values, the arguments of the function. So in this case, we are going to call update, any of the update objects, on our temporary. Okay? And then we are going to say, okay, and then conjunct all of those calls. So if any of the calls returns false, automatically the whole expression returns false. If they all have succeeded, then we go into the if. And in the if, we just do what we previously defined, swap this and temporary. In that case, we return true. Otherwise, we return false. And if we return false, we haven't updated a single field in our user. So this DSL is a beautiful DSL. Even if you might not like the syntax. It's really small, it's easy to implement, and the best part of it is that it's context-free. So all the nodes that we've seen for update actions had no idea that other nodes exist. They didn't even know that they have a root. And if you define your DSLs, try to make them context-free, it will be much easier than if you don't. So what to do if we are not context-free? There is a new feature planned for C++20, which was talked about yesterday by Alex, and those are ranges. Ranges are also a DSL. Somebody took the Unix pipe syntax and ported it to C++. So the latest try was obviously Eric's, but before Eric's there was Boost Range and a lot of other libraries, including some from ThinkCell, I think. So we have a DSL that says we have a source of data, and we pipe it through a series of transformations, and in the end, we can have some consumer, which will evaluate the data. So naively, we could say, well, this is the AST of ranges, because we have a source, which is the blue rectangle down there, and we pipe it through transformations, and in the end, we have the yellow rectangle, which is the consumer. Why is this a naive AST? Because ranges, okay, I'm going to skip this. This should be obvious. Ranges allow you to refactor your code, so you don't need to create a whole pipeline of transformations at once. You can just say, take this data source, apply these transformations to it, and just save it somewhere to a variable. Then you can use, again, the pipe to compose different transformations. So you don't have a source, you don't have a producer nor a consumer. You're just composing different transformations. And in the end, you can also have a transformations connected to a consumer. So no source, just transformations and a consumer. And then in the end, you can, again, compose all of these three into one single range. So the AST for ranges could look something like this. So any arbitrary binary tree, because the pipe operator is a binary operator, any sort of topology that, that a binary tree can achieve is something that your range can look like. And the problem here is that not only that we can have an arbitrary tree, but that different dots can have completely different meanings. So here they're all in green, but this would be more accurate. If you connect a source to a transformation, it also behaves like a source, right? If you transform values from a source collection, it's like we are having a collection of transformed values. On the right-hand side, if we have a consumer and we chain a transformation in front of it, it's like we got a new consumer. And lastly, if we just chain two transformations, that's transformation composition. They're not applied neither to a source, neither to the consumer, right? And in the end, if we connect a source to a consumer, so we have a chain that has both, then we can't chain it to anything else. So we have at least 4 different types of these circles in our AST. So the pipe operator can have significantly different meanings. In mathematics, this couldn't have been the same operator. In Haskell, it wouldn't be. We would have different types of all the operations because we are not going the Java way and inherit one superclass in all our transformations, sources, and everything else. We want to be as performant as possible, so a lot of template metaprogramming. And we can have an arbitrary complex AST. So what should we do? If we can just open one of the compiler books that are being sold outside, and we would see that if you want an arbitrary AST, you create nodes, and each node can have children. In this case, because we've said that it's a binary tree, we could have a range expression, can have the left subtree and the right subtree. Fine so far. And obviously, left can be a transformation, left can be a source, or left can be a proper sub-expression. Now the problem is that in this situation, we just know that which children of the expression we have, but we don't know what is the type of the expression. As we've seen on the picture, we can have different types of expressions. These circly guys are the expressions. For these things to work, usually you would declare something like a meta tag, meta information for your class. You can create a couple of structs. Just don't look them as structs. This is now template metaprogramming. Look at them like values of some kind. And for each of your classes, you just say, okay, a filtering is a transformation. So when you define a filter node, you're going to say that filter node has the node type of transformation node tag. Otherwise, we return true. So we have created a meta function that will check at the compile time whether something is a node for our DSL or not. Now we can create pipe operator, which is a generic, beautiful pipe operator, but we need to restrict it on certain types. If you just wrote a type name left, type name right operator pipe, it will be applicable to all types in your program. We want the pipe only to work on our nodes, this pipe. So we can just say, that for this template, we require that both left and right types are nodes. Now, obviously, the require is not a keyword of C++ 17. This is just a dirty macro which invokes std enable if. But since enable if is a really ugly thing to look at, it's much better to put it inside of a macro. And what's another reason to put it inside of a macro is that in C++ 20 we are getting concepts. So we'll be able to do this with proper C++ keywords. They won't be located exactly where the macro is, but they will have the same meaning and same semantics and the same effects. So we have created the pipe operator, which works only on types that are annotated as nodes. Now we can check if the left argument is not the producer and the right argument is not the consumer. Then this is a composition of transformations. Okay? So what we're going to return is a new expression, and we will put transformation node tag inside of it, so that we know that it's a composition of transformations, therefore it's a transformation, and it's not a producer nor a consumer. The next step, if the left one is the producer and the right one is not a consumer, then we can look at the new result as a new producer, transformed producer. The same goes the other way around for the consumer. And otherwise, we are going to return expression which is void, because we don't want to allow it to be inside of the continued piping. Is this fine for now? Now, one of the things that I haven't checked here, but it could be useful, is to forbid the left to be a consumer and the right to be a producer. So you always need to chain producer to a consumer and not vice versa. Now, the next step, so far, we've created just an AST. When we create a whole pipeline with the producer and the consumer, just like in the previous case with the transaction, we can then decide to evaluate it. We don't need to, we can evaluate it at some later point. But in this case, it would be quite beneficial to say, okay, from this point on, we are no longer in the AST. Now we are going to deal with semantics. So the question is, how can we evaluate an AST this complex? We have a tree, and we want to define a semantics for it. If we take the semantics that the range library has, it's something called pool-based semantics. The consumer asks for a value, and then that request is transferred to all the transformations in front of it until the value can be pushed back to him. Okay? For this, we would need an AST that looks like this, and not an AST that we've seen. But is this the final AST that we want? This is a trick question. It's not. This would be the AST if ranges were context-free. So if all the transformations didn't care at all about what they're transforming. When we want to evaluate a range, all the transformations need to know who their parent is, how to access the value of the previous transformation or the value of the source collection. So we don't have a normal tree. We can get a proper list where each of the items knows about its parent. So what's the idea? If we have a tree, the easiest way to flatten it out is to recursively collect all the items from the left subtree, all the items from the right subtree, and then just merge them. And we can do recursion during compile time as well, and pretty tree recursion. So we can create a lambda called collect subnodes, which checks if our current subtree is a proper tree, proper expression, then we are going to call ourselves recursively. Otherwise, we are just going to return a tuple that contains the current node. And then the collect nodes, the only thing that it needs to do is to collect the nodes from the left subtree, from the right subtree, and to concatenate the two resulting tuples. We can use fold expressions again. Now, for fold expressions to work, we need to have an operator. In this case, we don't have any operators. In the previous example, we had the ampersand. And here we just know how to merge two transformations with each other. We have a function for it, but we don't have an operator. So just create an arbitrary named operator. Whether it's a comma operator or percent operator, just use something that is rarely used in other parts of the code so that you know that this is a dummy operator, that it doesn't really do any division or anything else. And obviously, it's easier to grep than if you use some more sane operator. So when we want to connect a producer and a consumer, which are in the AST, they were separate nodes. Now we want to merge them. And we can have, for example, a function called widProducer, which merges them into one and says, okay, I'm a node, and now I know who my parent is. Okay? So we are returning a node that has some contextual information, unlike in the previous example, in the first example. And then if we want to evaluate all the nodes, we can just say return ... % nodes. And the fold expression, again, will just enlist all the arguments and put percentages inside. So far, so easy. What's the problem? We don't have evaluate nodes that receives all the nodes separately. We've just created a function that collects all the nodes inside of a tuple. So we have a single argument, which is a tuple, and not several separate ones. For this, we have the most ugly thing in the STL, but it's amazing. And it's called the index sequence. If we have a tuple and we need separate arguments, we need to have the way to still get a specific coordinate from a tuple. So we need to somehow have generated indices for all the values inside of tuple during compile time. And for that, is the thing that you use is the std index sequence. So we are creating a template where the first template parameter is the tuple, and then we have a variadic list of integers or unsigns. That list will contain 0, 1, etc. until till the n-1, where n is the size of a tuple. So if we have that, then we can create a dummy function evaluate nodes impl, which gets that tuple and gets an index sequence. Now we can call the fold expression and template pack expansion just by saying std_get index of nodes. This will generate std_get call for 0, std_get call for 1, std_get call for 2, etc., 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 and put percentages in between all of them. Okay? So whenever you have a tuple and you need to do some template metaprogramming stuff on it, just remember that the index sequence is the ugliest and best thing in STL. Now, this is a helper function. We need to create a function that just gets a tuple and calls this one. So what does it look like? We can call this dummy impl function, and we are going to pass the tuple in, and we are going to generate the index sequence that will be used to deconstruct the tuple. So for that, you have the make index sequence, and how many numbers that index sequence should have. The same number of numbers as the tuple has values inside. How do we get the number of values inside a tuple? Just with std tuple size v. Cool? Now that we've seen this, one question before we go to the next section. There is an alternative to the ranges pull syntax, and it's semantics, and it's called push semantics, where on the left-hand side, you have somebody who sends the values, and instead of the consumer asking for the values, it just gets any value that the producer produces. So instead of the request going from the last node to the first, here we would have a request going from the first and just being pushed through. Any ideas what would change in our implementation of the previous code? Who is talking? Okay, Sergey. Yeah, we would have, instead of with producer, we would say with consumer, which means that we would need to evaluate our pipeline in the reverse order. Okay? How can we evaluate in a reverse order? You can either use right associative operator for folding, don't, or you can just flip in the recursive tree traversal, just flip left and right, and then you're going to get the reversed list. And that semantics is usually used in reactive streams and whatnot. So what are the problems with ASTs? First, we have a lot of types. And the types, when you implement expression templates like this, can get quite huge. And C++ loves to put references everywhere, to put consts everywhere, etc. And you can have beautiful compiler errors because of a single character that you missed in some place. One of the things that I advise everyone to always do when doing any sort of template metaprogramming is to define a static assert called assert value type and put it everywhere in your code. For each generic type that you accept, assert that it's a value type. Just like the const is the good default, the good default is to say that everything is a value type. If later you decide, okay, in this case, this is better to be a reference, then change it, then remove the assertion. But by default, just like by default, you should declare everything as const, by default, declare that all your generic types are, in fact, value types. And my favorite function in the world, meta function, is the class called print types, which is not implemented at all. You just have a variadic template and define class print types. What can it be used for? When you have huge types like in expression templates, you often want to know whether it's a type or a const reference or a reference or a double reference or whatever it is. You can hover it inside of your IDE. Maybe the IDE is smart enough to write you out what the type is, but usually not, especially in these complex cases. My advice is to create a meta function like this one. And if you ever try to use it, this is like printf debugging in normal C++. When you write print types of, for example, std : vector bool reference, and try to compile, during compilation, this function will be executed, and you're going to get a printf message by the compiler saying that incomplete type print types of stud : bit reference. So now we know what std vector of bool : reference returns. The problem with this kind of printf debugging is that you can write only one type at a time, because the first type that the compiler encounters, it's an error and just drops out. If you want to do this trickery but write several types in several different places, some of the compilers are going to work with this, some not really. So just declare your class as deprecated. So it's not going to be an error, it's going to be a warning. And now you can have as many warnings as you want. Unfortunately, all the compilers I tested, only Clang prints out the whole type. GCC just as well. This is deprecated, and it doesn't tell you which type did you try to instantiate it with. But if you have Clang nearby, this is a great thing to have. Now, there is another problem with this, which is the same problem with hovering it inside of the IDE. When you get the output that compilers print out, or a tooltip in the IDE, it's not really readable. You get a huge type. Just imagine a huge tree flattened out in a single line. It's not readable. For short types like bit reference, it's perfect. But for a longer type, it's definitely unusable. So my advice is to create some, let's say, sed script or something like that. For all basic string mentions, just convert them to string. For all of your tags, just shorten the names so that everything looks prettier. And the most important thing to remember is to replace all the less thans and greater thans with normal brackets, parentheses. Because those are functions. Those are template functions, so why shouldn't we use normal parentheses instead of less than and greater than? And when you do this, you can just pipe through Clang format, and you're going to get a beautifully printed abstract syntax tree of your whole expression. I tried to replace, instead of normal parentheses with curlies. Clang format destroys the output, so don't. The best solution with Clang format is to replace everything with open and closing parentheses. And now when you see, this is an expression of several expressions. The first expression has a consumer, has a producer, which is a ping process. It's transformed with a lambda located in line 91 of the file, then transformed with another lambda, etc., etc. And if you just open this with a text editor or anywhere else, you exactly know the whole what the whole of your tree looks like, which is quite neat. And this is the perfect time, the most perfect timing that I've ever had. 45 minutes precisely and 15 minutes for questions. Thanks.
Thank you for the talk. Can you please choose a slide with make index sequence and index sequence? Why don't you use std_apply instead and just take variadic arguments and pass them through fold expression? It's the first question.
That's a good question. I have no idea. This was a little bit more complex code from production, where things are not as simple as this. And when I just compressed everything to a slide, I didn't even consider std_apply.
And the second question, in the basics part, you told about that DSL syntax. Does it work? How it works? I mean, it looks like just pseudocode or what?
Can you repeat?
Can you just open the basics where you use with? And yes, how does it work?
Okay, obviously there are some things hidden from the example, like what is name, what is surname, what is age. Yes, so obviously yes. They're not really a reference to members or anything else. They need to be instantiated values of this type. So in essence, that's the unfortunate part, is that for each of the field names, you would need to create an instance of the previous type, which is obviously something that you're going to do in a library, in a header that nobody sees, and with a lot of macros so that you don't need to write copy, paste, copy, paste. For example, it would look like define field member tester name, define field member tester blah, etc. Okay. So the point, this is actually a really great question, because one of the great things that I find with DSLs and any types library like ranges, etc., is that they have a lot of really ugly things hidden behind. The point is to make the main code beautiful. You don't care what's behind it, just make the main code readable and understandable. And I think that this, with all the ugliness behind it, this does it.
Thank you very much for this interesting talk, and I would ask, would you mind to create something like lenses for this case instead of this strange thing?
No comment. I'm going to leave it for you to give a talk on lenses on C++ Russia.
Okay.
But it's obviously a nice idea.
Thank you for your talk. I have a question about tag types. It seems like that you can use enum class for these tags instead of separate structs. And would it be better for compiler to use enum classes, because you don't have to keep lots of different classes, you just have one. And I haven't measured, but always when I need a tag which I use only in the template, I am using non-class template, non-type template parameter and enum class for tags. Is it better or worse?
Okay. My answer to that is probably yes, in this case particularly. The reason why I decided to use tags is twofold. The first one is that, for example, STL uses them everywhere because we didn't have proper alternatives before recently. So, for example, with iterators, iterator tags are still classes and everything else. Another reason is that the tag itself can have a more complex value. In this case, we just have 4 different structs which behave like enums. But sometimes you might want to put some contextual information inside of the tag value. And then you would really need to have a proper class. Okay?
Okay, thank you.
Hi, everyone. Thank you for such pretty tricks about debugging. And I'm just curious, what's the difference between consumer, producer, and transformer from the point of view, from the compiler point of view? And is it possible to deduce the type of the node automatically by itself? That would be a little bit, I think, difficult. You could create, instead of having a tag, you could detect, again, use the detection idiom to check whether something has a vid producer, If it has a vid producer, then it's probably a consumer, etc., etc. But I think that tagging types is a much more performant and efficient way and much more explicit than trying to create some heuristic which checks whether everything is done completely well. I think that tags make things much more maintainable in the future.
Thank you for the talk. It was really interesting to see some of the techniques you described. My question is, like, one of the major pain points when using C++ is compile times, and I believe like this approach is kind of painful in that sense too. So, have you measured like how painful it is to compile these type of things, and if it that much worse than like using alternative approaches, and if there are any like best practices to make this compile actually like faster or something? Thank you.
Thanks for the question. So the first part of the answer will be listen to the next talk by Oleg. As far as the performance goes, fold expressions are much faster than what we've used with template metaprogramming before. I don't think that there are any beautiful alternatives to this approach, because most of them involve a class hierarchy, virtual functions, which if you don't pay, I don't know whether it's an expression in Russia, but we have 2 words for bridge. And we have an expression saying if you don't pay it on a bridge, you are paying somewhere else on the second word for a bridge. So I would rather pay during compilation time than during execution. I know that compile times in C++ are a pain, but just look at the XKCD. It's compiling and you're fencing somewhere in the hallway. It's much for fun. So yes, this is going to slow down the compilation, but it's going to improve your speed of writing, and it's going to improve the execution time.
Еще вопросы?
Sergey?
Yeah, just more notes. Well, thank you for a talk first. And just a note, not a question, that you mentioned Zoltan in the last slide.
Mm-hmm.
And I just want to mention that the tool that Zoltan developed is really helpful for debugging templates, debugging with metaprogramming.
Yeah,
and
so Zoltan created, and some of his former students created a tool called Template and something based on it, which can, when you patch your Clang and stuff, you can do step-by-step debugging like in GDB for evaluation of your templates, which is really cool. So the next step after printf debugging is GDB debugging, and in this case, it's Zoltan's template. Thanks for the comment, Sergey, wherever you are, Seryaja. Okay, that's it. So, it's not. That's not it.
One more question about performance. Eric Niebler said that his ranges library compiles 3 times faster with GCC concepts implementation than with Svinaya. Have you tried to measure compilation times for different DSLs, for different real use cases, comparing Sphinaya and concepts?
I haven't, simply because I don't have the time to rewrite all the DSLs into concept-based code base, because I still cannot use C++ concepts in any real-world project. But I guess it would be faster, because just like lambdas are faster than std bind, built-in feature is faster than the library feature, so concepts are bound to be faster than the library-based solution like detection idiom.